Okay, let's start with this topic. Yesterday, we were finished with this hill climbing with this section, huh? And now we have to start this simulated annealing. So initially, we talked about three kind of searches: optimal search, global search, local search. So we have seen one example of local search, which was this hill climbing algorithm. And now we are moving towards this global search. So, so simulated annealing that we are going to see is uh, is a global search algorithm. And what is the definition for global search? We already know from our previous or from the first slide, we know that global search is something in which we explore the whole state space, okay? Which means the problem, whatever the states that problem is, we will visit or we will explore all the states or we will consider all the states, okay, to find the optimal solution. And now, from our previous discussions, we know that in global searches, we can say that our optimal solution is the other name for the optimal solution is global optimum or global maximum. So we have seen these different terms when I was explaining this diagram to you. What is global maximum, local minimum, and global minimum? I explained these terms to you already. So, so global search in which we will explore the entire state space to find the solution, and that solution would be optimal solution. The other name for this optimal solution is global optimum. And other name for this global optimum is global maximum. These are the different terms that we normally use for optimal solution in this category. We studied hill climbing previously. Most of you were not present in that lecture. Maybe you were sleeping, huh? Yesterday in the morning, huh? So, so hill climbing. Previously, we studied hill climbing, and we saw that hill climbing is in the category of local search. And normally, hill climbing does not provide a solution for the global maximum. Global maximum if we have a state at the top of this hill. And normally, hill climbing provides a solution only for the local maximum. Local maximum. I know that you don't know what is local maximum. Most of the faces you are here, you don't know. But I don't want to repeat it because this is your fault that you were absent in yesterday lecture. So, so I will go with these terms if you don't know. Anyhow, so hill climbing algorithm is incomplete. Actually, we don't have to say incomplete because the what is the definition of completeness? If some solution exists and if the algorithm is giving you that solution, that is called completeness. So then that algorithm is complete. This is what we know from our previous chapter. Hill climbing will always give us solution, but it will give us local maximum. It will not it will not guarantee us the global maximum always until we have our starting point on the hill or on that region where you have the global maximum available. Only then hill climbing provides us that global maximum, otherwise not. It always gives us local maximum. Due to this property that it always gives us local maximum, here we are saying it is incomplete. Actually, it is injustice with the hill climbing to say that it is an incomplete, huh? Because the definition of completeness is something different. But here we are saying that it is incomplete because if you are going to search global maximum and then it is not giving you that global maximum as it is the property of the hill climbing, then in that sense we are saying that it is incomplete, because it is always giving us local maximum and it will stuck on the local maximum. The people who have taken the yesterday lecture, they are understanding that what I am saying. So then what? So to get rid of this situation, we can do what? We can do a probabilistic walk, a walk in which the probability value will be involved. We will do that walk. How we will do that walk? By choosing successors. Successor means the neighbors of the current state. So we will select the next neighbors randomly. So now we are saying that in a searching algorithm, now if we are on a state, we can search the next neighbors, not too far states which are too far from that. No, I'm only talking about the neighbors of the state. So we will select the neighbors of this state randomly. Any, I can select any and then I can go on. So I can go with this approach, and also some probability value will be involved. If I will go with this idea, then this hill climbing can be complete. Then it means it will give us optimal solution, the global maximum. But it would be extremely inefficient, but it will take too much time to get that solution. Because if you have this state and the next states and the next neighboring states are maybe this one, and you want to reach at this one, huh? So if you are at this state, I can select this one, I can select this one, I can select this one randomly. If maybe the points are here, then I can also move this. I can also select this state, which is in the downward direction. And in this way, you will move on to this hill. You will not go on to this hill, which has the global maximum. So that's why we are wasting the time. The algorithm will waste the time. So that's why it is said that it is extremely inefficient. If you will go by selecting the states randomly. Anyhow, now another idea is, now we are going to combine the hill climbing with this probabilistic walk. We are the algorithm that we already studied, that is hill climbing. We are going to combine with this idea, which is probabilistic random walk. And when we will combine these two approaches, then a new searching strategy will emerge, and the name of that strategy will be simulated annealing. That will have the property of completeness, and it would also be, it will take less time, huh? So I know that I'm repeating this statement, that many of the faces, they don't know what these things are: local maximum, global optimum, what these things are. So I'm again saying it is not my fault, it is your fault that you were absent. So I'm moving next, and I only hope that when the algorithm will come, then at least you have to get the understanding of that algorithm. If you will get the understanding, then everything is okay. If you will not get the understanding, then there may be problem. Then I have to search some other strategy to give you the understanding of this algorithm. So now moving on to this simulated annealing. So what is the idea of simulated annealing? Annealing is the word from a theory which is existed in physics, and in physics there is some another field that is called metallurgy, about metals. So that theory is existing there. So normally you know that if you have to made something from iron or steel, if you have to build some product from that, normally you give high temperature to that metal, either it is iron or steel. When that metal will go into the form of some kind of a melting state, then you can shape that metal according to your need. And also when you are shaping, then you are also increasing the temperature down by putting some water on it. So that is the normal strategy if you are going to convert that metal into your product. So this is called annealing theory in physics. So here we are going to simulate that theory, okay? The name is simulate. We are going to simulate that theory in computer science. In computer science. So how we are going to, another idea is when you were in childhood age, you were playing with a bubble game which will have two small rods in it, and then there are many rings in it, and you were pressing the pressure button. Initially you were pressing hard so that your rings will go up, and then it will stacked on those two rods. And when you are in between or in the last stage of that game, then you will not put too much pressure. Okay, you are just playing sensitively with lower pressure. So the idea is, if simulated annealing has the same idea, that initially you will give the high pressure, and then with the passage of time you will lower the pressure, and finally you will reach on your optimal solution. So simulated annealing here, it is what initially we will start with shaking hard. So it can be some other game, okay? So initially the intensity of shaking would be high, okay? And you can call it that we will start the algorithm with high cost, or we will start the algorithm with high temperature if it is annealing. And then gradually we will lower the temperature, we will lower the cost, or we will lower the intensity of this shaking hard. So, and then we will try to reach our goal, which is our optimal solution, which is our global optimum or global maximum. So, we will adopt the same idea. So when we are going to adopt the same idea, so that's why the name is simulated annealing. Now, this is what we are combining: hill climbing and probabilistic random walk. So that's why it is a probabilistic technique, and this will approximate, or this will estimate, or this will calculate, or this will evaluate our global maximum or global optimum for any given problem, for any given problem or function. There is one advantage of it. What is that? Normally, simulated annealing is an algorithm. If you will give proper time to this algorithm, it will finally give you the global maximum or global optimum. But if you will not give this algorithm the proper time, the proper full time, if you will not give this algorithm the proper full time, it will do what? It will give you the second highest global maximum, or it will give you the third highest global maximum, or in simple words, it will give you the second highest answer, or it will give you the third highest answer. If you are not giving this algorithm the proper time, then it will not give you the highest answer, the optimal answer, but it can give you the second highest, or third highest, or fourth highest. So it will give you this answer which will be close to your final answer. So this is the advantage of this simulated annealing. So if you don't have extra time and your time is limited, and you are happy with second category solution, then here we are calling that solution the global acceptable global maximum, which means second category, not the final one. And if you are happy with the second category solution, then simulated annealing would be your choice in this situation, okay? Now let's see this algorithm. So this is the algorithm. Let's start it. Simulated annealing. We are passing some problem into it, and then we are passing some schedule in it. Schedule is a kind of a list in which you have the one column for the temperature T and the other column is for the time. Okay, is for the time. For the temperature initially can be high, so that's why I am putting it 100. Again, I am putting it 100. Again, I am putting it 100. And I can go like that. This is not necessary that you will repeat this temperature three times. It is up to you, four times, five times, whatever. But I am writing these values because this is what I have already practiced. Huh? So, and in this way, you can go on 98 and then finally you will reach at zero. Similarly, the time, initially it would be one, then two, then three, then four, and so on. And it will be, it according to this algorithm, it is going to infinity. Yeah. So inputs of this problem are what? The problem which we are passing and this schedule which we are passing. Schedule is what? It is a mapping. Mapping normally means a function. You will give time to it and it will give you the temperature. Huh? So mapping from time to temperature. So you will give time to it and it will give you the temperature at that time. So here you are putting the initial state of the problem. You have to take care. Okay, I will ask you at the end that you have the understanding of this algorithm or not. Okay. Uh, so now, whatever the problem is given to us, suppose we have this problem. What is happening? So suppose we have this problem. Huh? This is a state space. Okay. And on this state space, we have different points. So for example, I am drawing these different points. One state is here, another is here. So these are different states of the problem. And then one state is here, another is here. So these are one, two, three hills, huh? So where is the global maximum? On which hill we have the global maximum in this diagram? Hmm? So this one, which is the highest, huh? That is what it means. The highest, whatever the highest hill we have or highest mountain we have in this problem state space, that highest hill will contain our global maximum or global optimum. So this is our, now we want to reach here on this peak. So that's now this problem is going into it, into this algorithm. And then suppose that this is our initial state. Suppose this is our initial state. So then we are putting this initial state in this variable which is current. Huh? And then we have a for loop starting from t is equal to 1 to infinity. This loop is going from for the variable t, which is this one. So from 1 to infinity. So it will execute for all these values. Huh? So initially t is equal to 1, and then we are putting this 1 into this schedule, into this list, and then this schedule will return what? It will return 100. It will return what? It will return 100 into this capital T. So the value of capital T is now what? 100. What is your name? What you are looking at? What you are seeing? No, 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 no. You are looking on your phone, huh? Okay, anyhow. So that's why I said to you to come forward, because I experienced that most of the students, they are sitting behind and they remain busy in their own task. Especially this is true if the class, if the lab has a large area, then it normally creates a problem for me. But now this is not too much large area, so we can manage easily. So that's why you always have to come forward. So T, what is the value in T? 100 is the value in T. I will ask you question in between my discussion. Okay, so be alive, don't sleep. Okay, so what is the value of in capital T? 100. And then we are checking 100 is equal to 0. No, condition false. And then we will come here. And then we will right hand side will execute first. And here it is saying that randomly select neighbor of current. Successor means next neighbor. So what are the neighbors of this? This point is the neighbor and this point is the neighbor. Okay, there are two neighbors of this state, because this is my initial state. This I said this is my initial state, and there are two neighbors. One is this, other is this, and it you can select according to this algorithm. You can select randomly. If you will select this one, if you will select this one randomly, then this state will be stored here in this variable next. You can imagine that it is a xy graph and you have the value of the y is increasing like that. I don't know why it is not working. Okay. And then this point will have higher value, this point will have less value. Okay. Okay, now in the next you have some point which has the highest value. Then highest value, then what? Then the current. This is now my current, this is now my current, and this is now my next variable. Okay. So then next dot value minus current dot value. So when you will subtract the next from this next, when you will subtract this current, suppose this next has value 25 and this current has value 20, suppose, then 25 minus 20, you will have what you will have here? Minus 5, minus 5 or 5? 5, sorry. So because it is 25 minus 20, you will have 5. So delta E in physics, it means difference of energy. But here it is computer science, so you can remove this delta, okay? You can take this E as a simple variable. Otherwise, this delta E is a simple variable, okay? But this algorithm is written according to that annealing theory which is available in physics. So that's why the author used the same variable that are available in physics. So anyhow, so this is a variable. Now in E, you have the 5. Now, this 5 is greater than 0. Condition true? Condition true. When condition is true, you are updating the value of next into this current. So you are making the next state the current state. Actually, the meaning is, so then what? So now this state will become current, and this will, I can remove something. So now you are here. So now you are here after executing this statement. You are here at the top of this small hill. Clear up to this point? Everybody? Clear? But you are just sitting like that without any motion. Anyhow, so we are here now on the top of this small hill, and this point is a local maximum, okay, not global maximum. Okay, what will happen next? This else will not execute, and we will go back to this for loop, and here now the value of small t will become 2. And then this 2 will go into this schedule, and it will return you what? It will return you 100 again. So now in the capital T, we have 100 again. And then 100 is equal to 0, condition false. And then you have to select the next neighbor again, randomly. So now I am here. The next neighbors are what? The next neighbors, I can change the color so that it will be easy for you. The next neighbor are this point and this point from where we started. My algorithm can go here and there, wherever you want, because it is random. So now I am selecting this one. I am selecting this one because I want to go to my actual solution. Okay. So I'm selecting randomly, but I have just I have given you a trip towards this local optimum. Okay. But now we are going back to our actual direction. So now I am selecting this one again. And this has the value 20 and this has the value 25. Value. So I have selected this, and I have stored this this variable in the next. Now this is becoming next, and this is current, huh? And now the next statement is next minus current. So next is 20, current is 25, huh? Clear? I am assuming values. Somebody can say, from where I am getting values? I am just getting values from my own mind because these values are like that, huh? So 20 minus 25, then you will have minus 5 here in the delta E. And then you are checking minus 5 greater than 0. Condition false. Condition false. It means this will not execute and you will come here in the else portion. And here you are assigning next to current, but if this condition is fulfilled, if this condition is agreed, only then you are updating this value, otherwise not. And what is this value is? E raised power delta E divided by T. What is the value of delta E? Value of delta E is minus 5. And what is the value for the T? 100. And it has the E, huh? And if you will check, I don't have a calculator, so I will use it here, okay? You can use exponent or you can use E here, whatever you want, it is up to you. E raised power minus 5 divided by 100, huh? And if you will do something like that, you will have the value minus 95, huh? Minus 95. So this algorithm is saying that if you will get this value less than 1, slightly less than 1, okay, the words in literature is if you will get this value slightly less than 1, which means 0.72, 0.999, 9.99, huh? But not 1, huh? I am just saying, I am just giving some limit to you. You can take this limit from 0.8 to 0.99, but not 1. So the literature of this algorithm is saying that if you have this value slightly less than 1, then you can go for updating the value here. But if you have values far from 0.1 to 0.99, if it is higher or if it is less, then we are not going to do this assignment. Okay. So here my value is what? 0.95. So this is slightly less than 1, huh? So then according to that condition, we are going to update this value. And then we will put the value of next into the current. So then what? So now this will become our current variable. According to this statement, it will become our current variable or not? Because you are going to put the value of next into the current and you are making this state your current state. Then again, going back to this for loop. And now the T will become 3. And then from the schedule, the 3 will give you what? 100 again. So in the capital T, you have 100. 100 is equal to 0? No. You will come here, select random state. What are the neighbors? One is this, other is this. And now I am selecting this one. Huh? I am selecting this one, which is further in the lower direction. Further in the lower direction, not in the upward direction. So okay, I am going to select that. So I have selected and I have stored it in the next. And then here next minus current. Suppose the value of this state is, if it is 20, suppose it is 18, okay. Suppose it is 18. So then what in the delta E? So next is what? This is 18. Next is 18. Current is what? 20. So 18 minus 20, you will have what? Minus 2 here. Huh? You will have minus 2 here. Clear? You will have minus 2 here. Okay. So then -2 greater than 0. Condition false, and then you will come again to the else portion. And here you will check this first, and then if the value would be slightly less than 1, then you are going to do this, otherwise not, huh? So then what? Delta E is -2. Okay, then minus here you will have -2 divided by 100. So now check this. And it is slightly less than 1, okay, 0.98. So then what? So again you are going to do this assignment, and then this next point I can change the color further so that it will be easy. So then now this next point will become your current point. After having this assignment, this will become my current, and in this way you will go again to this loop, and then you will take the values again, and then you will take the difference. And for example, now for the next neighbor, now the next neighbor is this and this, and if you will select this, the value would be higher than this point, and it would be positive, and then you will execute this statement. And similarly, when this will be your current, then this is the neighbor and this is the neighbor, and this point has the higher value, so you will select that, it would be positive, and you will execute this statement. And similarly, finally, you will reach at here. And when you will reach at here, your algorithm also will go like that from t1 to infinity, something like that. And if your t is, suppose your t is 100 here, small t, huh? And then at 100, when the value of this capital T is 0, then it will become 0, and it will return whatever the value in the current is, it will return that state. From this discussion, you can understand something. What is that thing? That this algorithm will pick some state or move randomly by using this statement. It will pick some state or move randomly, and then it will accept the movement, whatever the move is, whatever the next state is, it will accept if the next state has the positive value. Okay, if the delta E is positive, huh? Then it means the next is higher and the current is lower, huh? Again, if your delta E is positive, it means this next has the higher value and this current has the lower value. The next has the higher value, which means that this is the next now, and you are here at it, and the next point is at higher point, huh? And then you will get this delta E always positive. When it is always positive, you are simply updating the states. So here it means that if you have an improvement, when you will have positive value, you are going to accept that change. You are simply updating the next into the current. And if your delta E is negative, when it will be negative? When your next is lower value and current has the higher value, then it will be negative. What happened? Then it will be negative. And when you will have negative value, then this else part will execute depending upon on this condition. And if this probability value is slightly less than 1, only then you are allowing. And this negative means also going in the downward direction, not in the upward direction. Why it has the meaning that going down? Negative means next is lower value, current has the higher value, which means current is at the higher point and then the next is at the lower point. Only then you will get negative value, and then you will move in the downward direction. So this algorithm is allowing downward direction moves only when you have this probability value slightly less than 1. If you will have some other value, it is not allowing you to to execute this assignment statement. That is what it is written here. That if your probability value is slightly less than 1, only then you are going to take that move. If it is positive, you are executing this statement. And if it is negative, you are executing this statement. Negative means downward direction, positive means upward direction. So what is bad moves in this simulated annealing? If you will read the book, then you will see this bad moves term there. Bad move means moving towards downward direction. Okay. If you are moving towards upward direction, then you have quite a chance that you will reach at the global maximum. But if you are moving down, then you don't have any chance. If you are moving down, then you don't have any chance. If you are traveling here on this hill, that you will reach on the global maximum. But sometime, now I am clearing this whole stuff, but sometime if you are here and then reaching here, then reaching here, and if you are in hill climbing will stuck here and it will give you this solution and it will not give us this solution, which is the global maximum here, if some other states are also here. So then what? If your algorithm is at local maximum, we need to move down. We need to move down. Either in that direction, either in that direction. If we will move down, only then it is possible that we will reach here on this highest peak. And when we will reach on this highest peak, then we can go easily on this global maximum. Easily on this global. So downward direction by the hill climbing was not allowing this downward direction. It was only going in the upward direction. But now this simulated annealing algorithm is allowing downward directions to move in the downward direction, but according to some probability value, which is slightly less than 1. So now bad move means moving in the downward direction. Moving in the downward direction. If your algorithm has this strategy in it, then it will not stuck on the local maximum. If you don't have this strategy in your algorithm, then it is like hill climbing. It will stuck on the local maximum, and then your algorithm will not give you the global maximum. And for this bad moves, here we are saying that this probability value E delta E divided by T, this probability value will decrease as the temperature will go down, as the temperature will decrease. When the value of temperature will go down, the value of the probability will also decrease. This is written in literature. How? I provided some examples here. If we have E raised by power minus 25 divided by 100, here the value of the temperature is higher, and then you are getting 0.7, and then we are lowering the temperature here. So this is fixed, but here we are lowering the temperature divided by 25, and then the probability is 0.3, and if I will make it 20, then the probability would be 0.28, and it is going to decrease. So what it means? It means when you are lowering the temperature, the probability value is also decreasing. This is, now you will understand this sentence. The probability decrease if you decrease the temperature. And what is the meaning? It means that the probability will only slightly less than 1 when the temperature is high. And when the temperature will become low, then we don't have that probability that we will consider to take that move. So this is far from slightly less than 1. Okay. I said I am going to consider the values, probability values, which are between 0.7 to 0.9. And I'm not considering any other probability. And this is 0.3. I'm not going to consider. When you will have this probability value, then we are not going to evaluate this assignment. So what it means? It means only for higher values which are slightly less than 1 we are going to consider. Then it means that in this algorithm, when temperature would be high, only then move in the downward direction is allowed. And for when your temperature is quite low, initially it is high. But when your temperature is quite low, maybe 60, 70 or something, then maybe this algorithm will not allow this downward direction move. So this algorithm will allow downward direction move only in the initial stages. In the intermediate stages or in the last stages, this algorithm will not allow the downward direction, move in the downward direction. So in this algorithm, we have this formula E delta E by T through which we are calculating this probability. We can call this formula the acceptance probability function. Here in this algorithm, it was not mentioned that if the probability value would be 0.7 to 0.9, then we are going to do this assignment. Otherwise, not. Yes, it is not mentioned, but I explain it in front of you. You can write these extra lines of code when you will be writing the program for it. Then you will write these extra lines that if the probability value from this formula, if you are going to get between 0.7 to 0.9, then you are going to execute this statement, otherwise not. This is one strategy. Other strategy is you can get the value from this formula and then you can generate random value between 0 and 1. So you have one value from this formula and the other value you will generate randomly from the machine between 0 and 1. Suppose the machine is giving you the value, for example, 0.6, and here you will have the value maybe 0.9, 0.98. Suppose. And this is the randomly generated value by the machine. Then you are going to do what? Then you are checking if this value is greater than this one, then you are going to execute this statement. If that is not greater, then you are not going to execute. That is another strategy that you can adopt. That is another strategy you can adopt, which is mentioned here. So you are going to generate random number between 0 and 1. And if the probability is larger than the random number, you are switching, which means you are going to execute this statement. Moving next. This is just an example because simulated annealing is not a simple algorithm. In this algorithm, we have too many iterations. It can go up to infinity. So this is an example of traveling salesman problem. This image is taken from the Wikipedia. And here you can say, okay, if this is your starting point, then the traveling man problem is what? Visiting all these, and these nodes are cities, visiting all these cities and come back here again to this point. And there is one condition that you can visit each city only one time. This and then these lines which are changing here, this is your algorithm is trying to find the optimal solution for you. And here you can see the temperature, it is now lowering, but when it will start again. So now it is ended, now started from 125. So initially the temperature is high, and this is delta E, okay? So initially the temperature is high, and then you can say when it is 0, then this algorithm is giving you finally the solution. Even there, I think if it is a GIF file, maybe I have the pause or something like that. Now you can see the temperature is 48, lowering down. So now algorithm is almost close to find the solution because the zero temperature is also now 8 and here 0. When it is 0, this is the final solution. This is the final solution. Huh? Anyhow, now what are the applications of simulated annealing? So this is general. So you can say anything. I can use the simulated annealing algorithm for fingerprints identification or for deployment of mobile wireless base station. The towers, huh? If you want to install mobile towers, which is a kind of a base station somewhere in the hills, then this algorithm will give you the guidance. Selection schemes inform animals population. From the animals, you want to select some animals to fit compartmental models with an application of fractional pharmacokinetics. This is something pharma medicine, huh? How medicine do in your body, okay? This is the study of that, okay? So you can also use that, this algorithm for that. Okay, traveling salesman persons, digital circuits, etc., etc. This is you can write whatever you want to write. Mostly it fits on. You can fit this problem in any domain where it can fit. Okay. Okay. Now the next is genetic algorithm. So now this lies normally the genetic algorithm always gives us optimal solution, and this lies in the category of optimal search. This is basically a evolutionary algorithm. There is another term used for this genetic algorithm is evolutionary algorithm, but leave that. So here we have made three divisions: local, global, and optimal. So that's why now we are seeing that genetic algorithm in this category, optimal category. Why? Because it will always gives us optimal solution. So optimal is what? Best possible solution. And what is the idea for this genetic algorithm? This idea of this genetic algorithm is taken from biology. Okay, biology. We have genes. So so those biologists have developed some algorithm for the genes, and we have taken that idea from that field to computer science, and then we have this genetic algorithm. And in the genetic algorithm, so we normally will have a pool, like this class is a pool and we are the populations in it, huh? And similarly you can consider some organizations or some country or some city, and then you have the population in it. Here I am going to take the example of humans so that you will understand, okay? But uh, in place of this humans, if if when you will get the understanding of this algorithm, then you can apply again this algorithm not only to humans, then any kind of data. But here I am taking humans as a example of data for this algorithm, just for the beginning to understand the algorithm. So in this genetic algorithm, initially we will have a pool. We will have some kind of a data set, okay? And that data set, we are calling it population. We are calling it population. And in that population, you will have the peoples, the members, or you will have the individuals, huh? For example, here in the class, if I call it population, then each member is called an individual. Huh? Each member would be called an individual. And in this algorithm, when you have the population, and in this population you will have the individual, then those individuals will compete with each other. For what? For resources, for getting the resources which are available in the world. So this competing for resources is something, a kind of a search, okay? Uh, and we will explain this strategy later on, that how they will compete. That how they will compete is the strategy of this algorithm. And normally in biology, the people who were in biology, they normally take some kind of a population. In that population they have the individuals. Those individuals normally compete for the resources in the world, and they mate. This is for according to the biology. So we are the generation of our parents because they mated with each other. So that's why we are here. So in the genetic algorithm, we will have something like that. We will adopt this idea. And in this genetic algorithm, only those individuals whose fitness is promising, who are fit, I can say, only they can survive. The individuals in the population who will not have that sufficient fitness, they will die out with the passage of time. Only the fit persons can survive in the population in this algorithm. I am just giving you the words so that you can understand the idea of this algorithm. Later on, I will start, and then you will, inshallah, feel easy that it is not that difficult. By the way, how many students have understood this simulated annealing? Raise your hands, please. Okay, good. Yesterday it was not a good experience, huh? But now it is good with. Okay. So in this algorithm, we will have populations. In the population, we will have individuals. Those individuals will fight for the resources, and they will do different things in this algorithm. And only those individuals will survive who would be in a fit state. Hmm? Yeah, survival of the fittest. That theory of biology. That is again the theory of biology. Yeah. So only those individual will be successful in this algorithm who are fit, and only those fit individuals will be allowed to mate next, to produce next generation, or to produce next offspring. We are the offspring of our parents, okay? So now you will understand this word offspring. So then what? So on it means that only fit person are allowed to propagate their material to the next generation. In this genetic algorithm, only fit fit individuals are allowed to propagate their material to the next generation. Anyhow, let's see that. We will go now step by one. John Helland is a person who gave this idea for the first time in 60s, huh? In 1960s. So this is a population based algorithm, and in the population we will have the individuals, we know that. And initially this person John has taken only, in the population it has taken only two members. So like mother and father, huh? So initially this person in biology has taken only two members, like mother and father, or like parent and child. Actually, this person has taken parent and child, only two members, and then they, from those two members, this person allowed that they can do crossover, they can do inversion. These are the different operations which can be performed like mating, for mating. If we have two persons, and if you are going to allow those two persons, they can perform these operations to produce next generation. They can perform these three operations. These two members can perform these three member these two members can perform these three operations to produce the next generation. And also for this mutation, crossover, and inversion, which two members are allowed for this? They normally, John normally introduced a fitness function which will calculate the score of the fitness for each member. For example, this figure is just giving you an idea that for this is generation T0, and here you have one member which is P for parent and another member which is C for child, and it has the fitness 5.6 and it has the fitness 9.1. And from these two members, the person or the member or the individual which has more fitness, only that is allowed to go to the next generation, and this the less fit member will die in that generation. So this child has the fitness value 9.1, so that is allowed to go in the next generation. And here now this child is becoming parent here, and then you have another child here which has the fitness 8.7, and here it is 9.1. So again this has higher fitness value and it is allowed to move on the next generation T2. And then here this has the fitness 9.1, and this child, which is a new child here, okay, new child of this generation, which has 11.1, and it is allowed now, this has more fitness and it is allowed to move next. And now this is now gone. And in this way, generation to generations can be produced. In this way, generation to generations can be produced by using the idea of John. This is also again uh, explaining the idea of this John, who gave the idea of this genetic algorithm in biology first. And here we are saying that in our population we will have these individuals, and we will represent those individuals with the strings. Now we are slowly moving that concept towards computer science, okay? So that's why we are saying it. So if you are going to consider genes, okay, then genes can also have the strings, but then it can contain A, D, C, adenine, something like that. They have their terms for the different parts which are available there in the DNA. So you will see A, D, C, F, something like that, the letters in the string of the genes. But here we have the binary strings, and this is a string for one individual, this is a string for another individual, and so on. And this is the population. From the population, we will select two members, through some selection methods. So here, selection. So in this genetic algorithm, you cannot do the selection simply, okay, take these two. No, there are some methods available for selection. So then we will apply those selection methods, and then we will select two members from here, and then after that we will apply the recombination process over these two selected members. And what are those recombination processes? Mutation, crossover, and inversion. What are these operations? We will see in the upcoming slides. Yes. Selection must be random? No, it is not random. We already said that only fit persons will be allowed. Then how it is random? Where is? I'm not understanding your question. In the population, what? These are the strings. Yeah, inside this population, this is your like a data set, huh? And from this data set, we will select through some methods. We will discuss in upcoming slides, not now. What are those methods? We will discuss what are those methods. We cannot select something from this randomly. So what is your question? It is not random selection, okay? It is not mentioned anywhere in this picture that you have to select random. No. These are the strings of different, like these are the IDs of different individuals in the population. And we will select from this whole population only 2 members using some selection methods. It is not mentioned here in this figure what selection method those are. We will see here when we will reach here. These are the selection methods. We will see them there. By using those methods, we will select members from it so that they can do the recombination process. And what is recombination process? These three: mutation, crossover, and inversion. We will also see what is mutation, what is crossover, what is inversion. We will also see. Just take uh, just show some little patience, and then we will reach there. We will reach there here. What is mutation? This is the picture diagram for mutation. Understand for the understanding of mutation, crossover, and inversion. Okay. So after this recombination, then we will have a new child. That child will also become the part of this population. Okay. And in this way, it will go on, and this algorithm will go on like that. That's why it is called evolutionary. That's why it is called evolutionary. And only fit members are allowed to to be selected and to do the recombination process, and then they will produce their children, and their children will also be with a fitness ratio. It and then the overall standard of the population, fitness level of the population will rise. Okay. And the weak members will die out with the passage of time. Anyhow, let's move on. We are just getting information. This genetic algorithm is not a single algorithm, it is a combination of different small algorithms. Okay. Some algorithms are here, some algorithms are here. Okay. It is a combination of different modules. Let's move on to further. So this is now kind of a flow diagram for the genetic algorithm with a little bit further details. This is abstract diagram. This is now a diagram with further details. So initially in genetic algorithm, we will have a pool, or you can say data set with a random population. Okay. We will have a population. Here, the word random doesn't mean that you are going to select random something. Okay. You have taken the member in the population. You have generated this population randomly. This is what here we want to say. You have placed every kind of person in that population randomly. And then after that, you will do what? You will compute the fitness of each member which is available in this population. You will compute the fitness of each member through some fitness function, And then after that, you will select 2 members from this population. We are still in the phase of population, huh? So then we will select 2 members from that population using roulette or elitist method. There are 2 methods available: roulette and elitist method. And then when those members will be selected, then these two members will be allowed to do this recombination process, which has the mutation, crossover, and inversion in it. And after that, a new child will born, and then it will become the part of that population again. So now moving next, let's see. So now here, population with members, okay, that is simple. Compute the fitness of the each member, okay, we can use some mathematical formula to calculate the fitness. But what is this selection process? Roulette and elitist. Let's see that. The picture here on the left hand side is roulette wheel selection, and the picture here on the right hand side is elitist selection. For example, this is your population now. You have the member A, B, C, D, and roulette wheel selection is what? If the fitness, if you have this score, if you have this fitness score 8440, then this score is representing what? So you will sum them up. How you can calculate it? You will sum up these all values. It will give you 16. And then you can calculate the percentage of each. This 8 is the half of this 16. So now A will get, from this wheel, A will get half of the wheel. Which means that from this whole week, half of the percentage is allotted to this member A. Or this member A has half percent of chances to be selected in this from this population due to this score. And then this 4. So this is like a 20%. If this is 100%, then this 50% has the chance for the member A to be selected from the pool. And then this 4, if you will calculate the percentage, it will give you 25%. And then this member B will have the 25% of chance to be selected from this population. Similarly, according to this score, 4, this is the total sum. If you will calculate the percentage, then you will know that this member C will have again 25% chance to be selected from this population. And this has the value 0, so it has the chance 0. Understood? Understood or not? Now, so that's why it is written here that the member, for the selection, that the member A will have 2 times the chance to be selected, and then member B and C has 1 time the chance to be selected. This is called roulette wheel method. And then we have the elitist selection. That is simple. You have to select the top 50%. Top 50, like student admitted in the class. If the maximum strength of a class can be 30 students, then you will make a merit list and you will select the top 30. So that is the same here. So here we have the population with member A, B, C, D. And if the fitness score is 8640, you will select the top 50, according to the score. Top 50 is this 84. You are not going into details of the calculation. No, you are taking the top 50. You will arrange them in a descending order of fitness, and then you will select the top 50. So top 50 is this one, which means A and B. C and D you are not going to consider. Even this member C has the 4 value, but you are not going to consider. So then what? 8 and 6. So then it is almost, the values are almost close to each other. So that's why member A will have 2% chance to be selected, and member B also has that the member B will also be selected twice. Member A will also be selected twice, and member B will also be selected twice, because 8 and 6 are very close to each other, okay, the values. Otherwise, you can have another idea that you can select these members, and then you can further, when you will select the top 50, then again you can apply this method, elitist method, over them, to then you will see these values, and then you will calculate that how many times this member will be selected and how many times this member will be selected. So you can embed this roulette wheel selection after this if you want. Now we are going to so from this figure we have now taken the understanding of roulette and elitist method. This is understood or not? Roulette and elitist, it is not that difficult. So, and now we are moving toward this recombination process, which has the mutation, crossover, and inversion in it. So, if you will look here only on this picture, this is a picture for the single point crossover. Okay. These two pictures, this is the crossover, this is also a crossover, but crossover has two categories in it. One is single point crossover, other is double point crossover. So here, single point crossover, here you will have the parent A, and here you will have the string for the parent B. Single point crossover means you have to identify some point in any one member, parent A or parent B. You have to highlight some point. For example, here I am highlighting with this line that I am going to introduce the cut here at this point after 3 binary digits. After 111, I am going to introduce this crossover or cut here. And if you will do something like that, then what will happen? So here, this diagram is little disturbed. I have to make the modifications. Just a minute. So now I have realigned these lines because previously it was not on a correct position. So now this is the single point crossover, and you have to do what? If this is the two members which are selected, then you have to select the single point in any partner. Where you want to introduce the crossover, you have to select that point here. For example, I am selecting here, maybe I don't know, maybe 3 and then 3 after 7th bit, maybe after 7th bit. So this line is giving you that hint. And if you are going to do that, then when you will perform this cut here, what you will do, you will move this remaining portion on the other side, and you will take similarly this portion to here. So the portion which is before the cut, it is, and then you will have two children will be produced after this single point crossover. After this crossover, two children will be produced, and then if you will look over the string of the parent A after the crossover, whatever the portion is before this cut, that is the same. But whatever the position of this cut is, you will go here maybe after the 7th bit. And what is the remaining portion is, you move that portion here. And similarly, these 7 bits as it is, 7 or 8, and then what is, you move this portion here. This is called single point crossover. And double point crossover. Again, you have to identify, or you have to draw these two lines now, which is double point. You have to draw these two lines. You have to draw two cuts on the string of the parent A or parent B. Now, for example, in the parent A, we have drawn these two lines. Now, this is the portion that you can modify with between these 2 points. Okay. And okay, this thing and this remaining thing is the same here in the children that you are getting, and only this portion according to the positions here, you are only changing that portion here. Similarly, for example, these are the 6 bits or whatever, okay, as it is, this remaining portion as it is, and this portion of ones you are moving to move here. This is double point crossover. Understood? It's easy. Understood? Anybody who didn't get the point yet? And then what is mutation? You have heard the name of mutation in the movies. X-Men, huh? X-Men 1, X-Men 2, X-Men 3, mutation. And in biology, this is what your surgeons are doing in developed countries. For example, if you have the chromosomes in humans, and if we have the disease genetically existing in any family, so when the new child normally born, what they do in the hospitals, if they have some genetic disease, they cut their chromosomes in half, and then they replace this to here, and they will replace this to here. Okay, they can do, or you can simply take the genetic information of parent to this. They will do this with the child, because we have all the information always in our genes. We have the DNA is available all the time, so they can do this. The surgeons are doing this surgery uh, in a newborn babies with their chromosomes. They are playing with their DNAs, gene, and with the genes. If they want to remove diseases uh, from some generations. Anyhow, here mutation. You have the parent A and the parent B. This is the string for parent A. This is the string for parent B. Mutation is just changing only one bit and then getting the next generation. Okay, changing only one bit in the, I can say, in the string of DNA, or you can say this is the string of a DNA of parent A and this is the string of a DNA of parent B. But actually, it is not according to biology, because if you will see the string of DNA, then it will have A, D, C, some letters in it. Okay, if you will apply mutation, then you can change only one bit here in the string of parent. For example, here we are changing that 1 into 0, and then you are getting the new child. Similarly, here from this string, you are changing this bit to 1 and you are getting new child. This is mutation. This is mutation, huh? Hmm? Randomly, yeah. Mutation is randomly. If you like random, mutation is randomly, okay? And then inversion. You have the parent A and the parent B. This is the string for parent A, parent B. Inversion. Inversion is changing bits from 0 to 1 and 1 to 0 more than 1. In mutation, you can change only one bit. But in an inversion, you can change more than one bits together. But those bits normally should be in a sequence, huh? But I think it is not compulsory in a sequence. You can. So, for example, here we are changing the bit, these two bits into zeros of this parent beta, of this parent string. We are changing only 2 bits. And from parent B, we are changing these 4 bits from this parent B, and we are getting these children. So this is now the mutation, the crossover, and the inversion. So your genetic algorithm can perform these three, can perform any one of these three or any two or something. It depends. It depends. So I will start, inshallah, next from here, because here this is the termination criteria. We obtained some information about the algorithm, that it will have a population, then it will compute the fitness function, then it will select parents, and then it will perform the recombination process, and then the new children will also become the part of population, and in this way it will go on and go on like that. But the question is when it will terminate. Okay. But the question is when this algorithm will be terminated. So that is the question, and we will start from here. Okay, inshallah, next.